Okay, so hello everybody. Can someone confirm if you can hear me? Just to see. Nobody can hear me? One.
You should unmute your microphone.
Oh.
On Zoom.
On Zoom.
Yeah, thanks.
Okay. It was muted on Zoom. Okay, so now people can hear me?
Yes, we can hear.
Okay, good. Thank you. Yeah, we told me it was unmuted already, the microphone, but then the Zoom also. Many things. Okay. So, hello everyone, and welcome to this lecture. So it's lecture 12 already out of 15. So we are approaching the end here. So what we are going to do today is one of these nice little intermediate lectures. So we proved last time the residue theorem, if you remember. And today we will go through some applications of the residue theorem. So this will essentially mean to applications to real integrals. So integrals from typically minus infinity to infinity of some function or something like that. And then the second thing we will do, which is actually what we will start out with, because the integrals you can go on forever, so it's best to take it at the end. So the first thing that we will do today is to see some more theoretical applications of the residue theorem, namely to the argument, what's called the argument principle, and a very closely related corollary of the argument principle is the result usually called Rouché's theorem. Okay, and all of this is also on the topic of the homework, so I want to make sure I can cover the second part, which is why I start with it. So let us just recall the residue theorem. So I just wanted to write it on the board so that everybody remembers. So suppose that f of z is analytic except for isolated singularities. Okay. Which could be essential. So poles are essential singularities. Aj in a region omega. And then we had the formula 1 over 2 pi I. So we could integrate. So gamma is any closed curve. We got that this was the sum of the product of the winding numbers and the residues of this function in the point Aj, where the sum runs over all of the singularities inside gamma, and we said last time that there's a finite number of these. Okay, so this is true for any closed curve. Gamma, which is homologous to 0 in omega, and a second important thing not to forget, and such that the AJs are not on this gamma. So this can sometimes happen, right? So especially when you apply it to the real integrals, it could happen that you would like to take some contour, but there is some pole, maybe, or some essential singularity of a function you want to integrate that's on this contour that you want to pick. So it's important to remember this part as well, that you don't want the singularities to be on the curve gamma that you choose. Okay, and this hypothesis with homologous to 0, it's there because you remember that the residue theorem was a direct consequence of Cauchy's theorem, and this is the general form that we stated for Cauchy. Okay, so now let's start with this, this topic, the argument principle. And as I said, then, later on, once we are done with this topic, it will take, I don't know, maybe half the lecture, something like that, very roughly. Then we will do some integrals with the residue theorem. So the problem here, problem or the question of interest is the following. So how many zeros and poles? So maybe let me make a drawing first. So you take some curve gamma here, and then they have some color, and then you have some zeros. I mean, maybe red is more poles, perhaps. You have some poles here in red, and you have some zeros in blue. And then you wonder how many zeros and poles are inside this curve gamma. So you want to count what's inside, but we don't want to see what's outside. Okay. So if you ask this question, so how many zeros and poles so for a given meromorphic function, of course. So imagine you had a meromorphic function. So how many poles does it have inside a given contour gamma? So this is the question. And it turns out that we can use the residue theorem to answer this question, which is maybe not very surprisingly, because if you see the residue theorem, it will pick up, first of all, it will only see things that are inside of gamma, because otherwise the winding numbers will be 0. And then, okay, we will go through the proof now, and it will explain quite well the relation. But we might still call it in my note that this was magic, which it might seem to be at first. So these zeros and poles are counted by the integral, following integral, f prime over f. So of course our given meromorphic function is then the one called f. Right? So it will be counted by this integral. If you integrate this kind of derivative of the logarithm. And the more precise version of this statement is then what is called the argument principle, which is one of the well-known theorems that one should go through in a course in complex analysis. So the statement is the following. Suppose that f is meromorphic in some region omega. And now instead of just saying singularities aj, we say that we have zeros aj, and we want to distinguish zeros from poles for this meromorphic function. So zeros aj and poles bk. Okay, then we have the following formula. So if you integrate along gamma, this quantity that I promised would be, in a sense, counting the zeros and the poles. So we'll see what we mean by that. So what we mean is that this is equal to the sum over all the zeros of the winding numbers of this thing, minus the sum over all the poles of their respective winding numbers. And this is true for any closed curve gamma, which is homologous to 0, and such that the aj's and the bk's are not on gamma. And we ask all of this business here because we want to apply the residue theorem in the proof. Okay, so the remark. So what is the relation with what I just said? So in what sense does this count the number of zeros and the number of poles of this function? So let me just remark on this here. So of course, this is a special case of this theorem, or a special consequence in case these winding numbers are always either 0 or 1, right? So it means that we have this kind of picture and we don't have something that winds around many times around these zeros. So the remark is that if the winding numbers are equal to 0 or 1 always, and the same for gamma bk, then this right-hand side in the equation, so this thing in the identity, it equals the number of, so then this will be 0 except at every 0 where it will take the value 1. So it will just pick up a value 1 for every 0 you have. So it's the number of zeros of f. Okay, and except for the ones that are outside gamma, it will still pick up 0. So it's the number of zeros of f inside gamma. And then what I pick up from here is, again, then the value 1 for each pole inside gamma. So it's minus the number of poles of f inside gamma. So this is the relation. So this is what would be maybe the most common application of this theorem to say that you are in this case. So any questions about this statement before I go on to the proof?
Professor.
Yes.
It seems that the derivative of f is counting the zeros and the f of g is counting the poles in the denominator. I'm sure you will talk about it in the proof, but why on? Right, that was cancelled out. Sorry.
Okay. Okay. So let's go through the proof. I didn't quite understand what you were getting at, but ask again if after the proof it's not clear. Is that okay? Okay. So proof of the argument principle. It's a direct application of the residue theorem. Okay, and you will see how this comes in now. So we have two cases. So, I mean, first we say what happens if f has a 0 of some order, and then what happens if it has a pole of some order. So, if f has a 0 of order h, okay, at some point a, okay. Assume we have this. Then what happens? Well, we know by the power series expansion, I guess, in this case, that f of z can then be written, so I can factor out this z minus a to the order of the 0. I can write it like this times some g of z, where g of z is analytic, and g of a is not 0. So again, this is the trick that we use over and over again. It's elementary to see from the power series expansions, but you have this kind of thing. So then we wanted to know what was f prime over f, because we wanted to compute this integral. So okay, f is equal to this. Then let's look at what happens to f prime. So then this picks up, sorry, that was one step too fast. So it was equal to h times this times g of z plus, now this is just the product rule, g prime of z. And now I just divide, so this means that I can just see look at f prime divided by f. Okay, so I take this divided by what's up here. So from this term here, I get h divided by z minus a, and everything else cancels, including the g's. And then I get plus, from the second term, I get g prime over g. Right? So I get this. Okay, and now we note that we said here that g of a was not 0 because of our assumptions that h was the order of the 0. It implies that g, by construction, is not. So g of a not 0 implies that g prime of z over g of z is analytic in the neighborhood of a. Okay, and this implies in turn what? So what is the conclusion? So I say that this one, because the denominator is not 0 close to a, this one is analytic close to a. And what can we then conclude about the residue at this point?
Zero is residue.
The residue is 0, yeah. So this, what you're thinking is probably that this part, which is analytic, contributes 0 to the residue. But if we look at the residue of the whole thing, we still have this part, right?
Yeah.
Which then contributes with h. So this implies that the residue of f prime over f in the point A is equal to h. Okay, so this was a way of computing the residue, a way of finding the residue. Is this clear?
Yes.
Very good. Thank you. So if f has a pole of order k at the point B, okay, so earlier we had a 0 of order h at the point A, now we have a pole of order k at B, then we do a very similar thing, right? So then we do, so earlier we had f of z of this form, but if you have a pole of order k, then what does this imply about the shape of the function? Well, it's similar, but now we had the Logan series expansion, and the thing will then look like this. Okay, where again, g is analytic, and g of b is not 0. Okay, and then we get, in the same way, we get that f prime of z over f of z, so I won't do it again. So we get that this is minus k over z minus b plus g prime of z over g of z. And this will imply, as before, that the residue of f prime over f, but now in this point B, where we had a pole, will be then minus k. And this minus sign is sort of essential, because this is where, I mean, this is why you will get the difference of the zeros and the poles. So the way you can summarize this is that the order of the poles is counted negatively in the contribution to this integral, whereas the order of the zeros are counted positively when you add to this integral. Okay, and by the way, so when I say I'm counting the number of zeros and the number of poles, it could happen that you have not a simple pole or something like that, but you could have a double pole, a triple pole, a double zero, a triple zero, and so on. And then they will be counted, if you have a triple zero, they will be counted 3 times, as you can see from this. It would be a 0 then of order 3, and then you would pick up this h here from the residue, which would reflect the multiplicity of this singularity, as we say. Okay, so far so good, but now how can we conclude the theorem? So now all that's left to do is just apply the residue theorem. So we computed in the zeros, we computed the residues, and in the poles, we computed the residues, so this f prime over f. And so by the residue theorem, we get the following then, that if I write down 1 over 2 pi I, and this integral, then this is equal to, okay, so I just write down again the definition then, from the residue theorem, plus, here, okay, so I separate the zeros and the poles. And now we said that this thing right. So I think there's some mistakes. I think when I stated it just with, I assumed that the order of everything was 1, right? Because you see what will come in here now is then this is the order of a 0. So this is what I would call the order of f at z equals aj. And this is the order at z equals bk of f. And so actually what we get, so I apologize for this, I will change it. So it's okay. Sorry. So now I will explain. I realize now what I did. So it's correct actually, but what you get is this up to multiplicity. It's just this remark. I'm sorry, I got confused there for a moment. So it's equal to this plus this if you assume that each 0, I mean, when you write this aj, so you write a1, a2, a3, and so on, that you separate them. So if you had a triple 0, you would write the same point 3 times. And hence you would then sum over, so instead of putting the order here, which might be 3, and summing once, you just sum 3 times over it. So it just, you know, up to this multiplicity here. So actually it's a bit dangerous because it has to be interpreted correctly. So I should be more careful. I should write here, so up to interpreting this multiplicity of the zeros and the poles correctly. So to reiterate this theorem that I wrote down, it's correct if you say that, okay, in case you have, you know, 1 over z squared, then you would count, and I ask you what are the zeros, aj, then the correct answer would be 0 and 0 again. You see? So, I mean, this is a common convention, you know, counting things up to multiplicity. Anyway, from a residue theorem, you can, this proof is actually very, I mean, it's a very nice proof and a very clear proof that you can easily redo. So then you understand what is the meaning of all these things. Okay, so it's counted correctly up to multiplicity. We can interpret it in this way. and then we would be done. Okay, I hope this didn't confuse you too much, this discussion with a multiplicity. Are there any questions about this proof? While I erase the other board. Okay, good. So, I mean, if you're unsure about it, you can, I think, for sure understand the proof, and then you will see what is the meaning of the statement. So now, let's take a look again at this argument principle, and let's see a useful interpretation of this theorem, which is sometimes used in applications, and in particular it's used in this Rouché's theorem. So if you let gamma, so now for the moment this is something we haven't seen in a while, but let gamma just be a curve which is not closed necessarily. So gamma is a curve like this. You have gamma of A, you have gamma of B, start and end point. And then, if we look at this integral, so we write down the integral that appeared in the argument principle, and we see what it equals. So again, if you go back to the first lectures on integration, you would see that this was equal to this, which is then, which I can write in the following way. So yeah, so it's 1 over 2 pi I, integral from A to B, and this is just the same denominator up there, but then, oh, I'm sorry, yeah, it's not the same. Yeah, so it's this times this, and then down here, let me just put f of gamma of t dt. And now if I introduce just some notation, so let me say that sigma is f composed with gamma. Then if I use this notation, then this is actually equal to 1 over 2 pi I, integral from A to B of sigma prime of t over sigma of t dt. But now going back, what is this? Well, it's just equal to, so if I integrate over sigma instead, so I started out with an integral over gamma of f prime over f, and now I'm going to go back to an integral over sigma, which is then this image of this curve through the map f. And what should I write in the integrand here? Anyone? So I had, if you just go backwards in the definition,
1 on Z.
1 over z, exactly. Or 1 over w, dw. I will choose this later. That is correct. So it's equal to this integral over sigma. And again, I repeat that sigma, you should think of it as you have this curve, and then you apply the function to it, so you get some other curve that looks something like that. This would be sigma. I'm just drawing something at random, of course. It's just an abstract example. But it might look something like this. It doesn't necessarily start here either. So you have some image curve, and then you integrate 1 over z, or 1 over w, along this new curve. And this gives the same result as what we just saw in the theorem. Okay? And then we know that this kind of integral, 1 over w, what does this do? So we should recognize this from something that we have seen. Anyone tell me what it is? So the hint is winding number. Is this a winding number?
It's not necessarily winding number because it's like sigma is not necessarily closed.
Wait, sorry.
Sigma is not necessarily closed, and we define the winding number over gamma to be closed curve.
Uh-huh. Yeah. Yes, you're right. So let me put it this way then. So this should anyway be interpreted as, I mean, I trust you that this is what we did. I don't remember exactly. But this, you can interpret this anyway as the winding number. I mean, so if you imagine that gamma was closed, then you agree with me that this is the winding number around 0 of gamma. Right?
Yes.
So gamma closed. Then this is this winding number. And it means that in order to compute this integral f prime over f, one way to do it is if we could somehow easily determine, it might be easier sometimes, to determine the image curve and then just count how many times it winds around 0 in this case. So this is a very sort of interesting application, interesting interpretation of this result. So we might see an example of this in a little bit. But first, let me go through. I mean, actually, let's see here. So you know, an example of this would be to let me give you an example right now. After all, changed my mind. So the example of the argument principle would be, can we find the number of zeros of, let's say, some polynomial like this in the right half plane, so in the plane which has positive real part. So this would mean that we are looking at, so this is obviously, it's a polynomial, so it's an entire function, right? And then we just want to find all of the zeros that it has in the right half plane. And now I'm claiming that we can use this remark that I just gave about this image curve sigma to actually do this kind of thing. Of course, because this is a polynomial and it's kind of easy to understand. So let me just sketch the solution. So what we will do is we will consider a large half disk, or a large half circle, like this. So this will be the point IR. Okay, so IR minus IR, this would be R. So we consider this this curve, or this, actually it's a large disk, so it's a large semi-disk. And we look at the number of zeros inside this this disk. Consider the number of zeros inside the closed disk, so more precisely of some radius r, intersected with the right half plane. So where the real part of z is greater than 0. Okay? And then, of course, when r is sufficiently large, this will find all of the zeros of this p because it's a polynomial, so we know there are, 5 zeros. So there cannot be some sequence going off to infinity. So this is a large half disk. And then we want to estimate how we want to now get a sense for what the image curve looks like, right? So here we have to see on this part, So this consists roughly of two parts, right? You have the curved part and then this straight line going down the imaginary axis. And then you have to see how the argument changes as you go along these curves. Okay, so let's call this part maybe LR for the line, and this would be the something, I don't know, the curved part, so CR or something. I don't know what I called it in my notes. I'd have to look. But anyway, so along this LR, so the line where Z is equal to just IY, then we can see that P of IY is equal to the following. Okay, so I times y to the fourth plus 1, and all of this plus 1. So this is the real part here, and the imaginary part is here. Okay, and this one goes to infinity as y goes to plus infinity, and it goes to minus infinity as y goes to minus infinity. Okay, and at this point I should say that I'm not going to write down all of the details now, so I just want to give you the idea, and then you can, convince yourselves that this is true. So you just have to, you have this polynomial, so it's a simple function, and you have to convince yourself what happens when you look at the image of this line under this function. Okay, and the claim is simply that the argument, if I look at the argument of P of IR, which is a point in the complex plane, and I look at the difference between this and P, the argument of P of minus IR, then what I'm claiming is that the difference will be exactly pi. So one will just go off here and one will go down. The difference will be pi, but actually it will be minus pi, because here it will be because of this orientation. So you can check this. So I'm not saying that this should be obvious, but I'm claiming that this should be minus pi. And then you can check in a similar way, and this is easier to believe, I think, that what would happen when you go around this curved part of the circle. Well, essentially the action, what's happening to a point here, or to any point, is just that you multiply the angle by 5, exactly if it was Z5. And now you have this Z plus 1 part, but since R is very large, it will act roughly as Z to the power 5. Okay. So I'm actually allowing myself to do this in a sort of approximate / sloppy way. And the reason for this is that when I count, when I want to determine how many times the image curve winds around 0, then the secret is that I know that the number of times it winds around will be an integer, right? I mean, it will be an integer multiple of 2 pi, but the argument has changed. So if I just sort of by an approximate argument can say that, okay, it's roughly, the change in argument is roughly 4 pi, then it has to be exactly 4 pi, because it's a closed curve, so it has to wind around an integer number of times. Okay, so on the half circle, defined by this, and real part greater than 0, then P of Z is equal to, so we'll look at it in this polar form, right, in this exponential form. So every Z is of this form for some angle theta, which is the argument. And this is then equal to, so let me put it like this. So let me break out the dominant part. Okay, and then the point is that this thing that I wrote within the parentheses, so this is exactly what I said, so I just have to tell you that this is approximately 1, as R is very large. And it means that the dominating behavior really comes from this, which will lead to the change of argument. So here theta, I can say that it's from minus pi half to pi half, because I was in the right half plane. And then the point now is that the argument of this thing is then in the interval 5 pi half, minus 5 pi half to 5 pi half. And in fact, we have that we change in the argument sorry, what I wanted to write was this. So I wanted to look at the start and, I mean, points that are very close to the start and end point of this, where it meets the axis. So I wanted to look at I times, so pi half minus epsilon. And so something that is very close here. Okay. And I wanted to compare this with what happens to a point that's very close here. So this would be P of Ri minus pi half plus epsilon. Okay. And this would be, just again, very hand wavy, right? So it would be roughly 5 pi. So I don't write down anything precise about this approximation. Okay. I'm just saying that as R becomes very large, we can all see that it behaves roughly like this, like z to the power 5, in other words. And this one would change the argument by multiplying everything 5 times. The change in argument would be roughly 5 pi for some very large R. And then, so the total argument change can then be estimated, so approximately it is minus pi, which was the contribution from this axis, so we never explained exactly why, and this, so it was approximately this, so it's approximately 4 pi, but of course the change in argument has to be a multiple, an integer multiple of 2 pi, so it means that it's exactly 4 pi. And it's because this curve that we consider, this gamma r or whatever, this total curve, that this is closed. Then total change must be an integer multiple of 2 pi, so it's exactly 4 pi. And this means that 4 pi is the value of the integral now in the, so backtracking everything, it means that 4 pi, no, sorry, it means that 4 pi, yeah, so 4 pi is this integral, but it means that the winding number, if you change the argument with 4 pi, it means that you wind around twice, right? Up to orientation is important. The winding number is 4 pi divided by 2 pi, so it's the number of laps that you take, so it's 2. And this means precisely that P of z has 2 zeros in this right half plane. Okay, so the purpose of this example is not, that it's supposed to be super rigorous again. I just want to mainly illustrate to you that this kind of stuff is possible to do with the argument principle. Okay, And then I would urge you to try and fill in the gaps at home here. But keep in mind that the fact that I was not very precise on this approximately 1 and so on, I mean, really, this is okay because of this observation that it has to be an integer because the curve is closed. Okay.
Professor,
Yes.
I'm not sure I understand the part where you subtract the arguments.
Where I subtract the arguments. Yeah, so what I want to look at is, so what I want to do is I want to understand the winding number. So this is what I can say that is precise, right? So you have a polynomial, so a simple function, which is entire in the plane. You want to understand the winding number of the image of some half circle under this polynomial. And then you have to, try to be a bit clever or whatever to try to understand the difference in argument, okay? So I propose to divide it into these two parts, but at the end of the day, it's a polynomial and you can understand it in many other ways. So you can try to choose your favorite way to understand this thing. So, I mean, the takeaway is anyway, you have to try to understand in whatever way you want how many times the image curve winds around 0. And this is exactly what I'm trying to do with this difference of the arguments, because, if I have some curve and I look at one end of the curve and another end of the curve, and I see that at one end the argument is 7 pi, let's say, and at the other end of the curve it's minus 5 pi, well then I can see that I have traveled the distance of 12 pi, so to speak, so I traveled 6 laps around 0. But then you also have to take into account the sign, because depending on whether I go counterclockwise or clockwise, it will pick up a positive or negative sign, this change in argument. But this is what I'm trying to do. So I'm trying to say that when you're on this straight part, I'm saying that you actually go clockwise half a lap, and when you were on the semicircle part, you actually picked up 2.5 laps counterclockwise. And since the winding number, if something goes 3 times around in one direction and then 1 lap back, then they subtract and the total net winding will be counted as 2. So this is what I'm doing. Is that somewhat of an answer to your question, or at this point?
Thank you.
Yeah, okay. Great. Okay, so now let's do Rouché's theorem, which is one of these again, one of these classical miracle theorems in complex analysis, which seem very strange at first, which is not, it's not unique in complex analysis in this regard. Okay, so again, the remark was that, so if we understand the image curve, so just to reiterate again what this whole remark and this example was about, so if you understand the image curve, sigma, which is f composed with gamma, where gamma was the curve we were given in the beginning, then this can give us, without actually computing anything, the integral along gamma of f prime of z over f of z dz. So, it can go both ways. It could be easy to compute this in order to understand the image curve, or sometimes, maybe like in this example, you can compute the image curve to get this integral. Just to underline that it can go both ways in theory. And now, from all of this argument principle business, you also have this, now time to state the Rouché's theorem. So what does it say? It says that gamma is a closed curve homologous to 0. And we also assume that the winding number is 0 or 1 always. So it doesn't wind many times around some point. It's the closed curve so that the winding number is always 0 or 1 for any z which is not on gamma, okay, in which case we did not define it. And now this Rouché's theorem, it's about comparing the number of zeros of two functions. So we need two functions, f and g. Suppose f and g are analytic on some omega, and assume that they satisfy some hypothesis here, which might seem strange at first, to say the least. But let's assume that the absolute value of their difference is less than or equal to the absolute value of f, so the first of these functions, if you want. So when you apply this, you always have to, keep your head straight in what is f and what is g, and which one should I choose to be my f, and which one should I choose to be my g. So this thing should be true, but here comes an important detail. So this should be true on gamma, okay? So not everywhere, but just on the curve. So typically gamma might be a disk, and you want to then have this estimate on the boundary of a disk. And then the conclusion is that f and g, they have the same number of zeros inside gamma. Is someone saying something? No, okay. I think it was somebody outside the room. I heard something very vaguely. Okay. So then this is equal to the number of zeros inside. So we have the same number of zeros inside gamma. Sorry. So how can we apply this, first of all? So application. So let's assume that we take g of z to be z to the 9 plus 5 z to the 3 plus 2z plus 1. So let's study another polynomial in this case, okay? So the question is, somebody asks you, how many zeros does it have inside some well-chosen region? So, well, let's actually say, so in the region outside of the unit disk. Why not? So how many does it have outside? This is the question. We want to count the number of zeros. So of course we know in total there are 9, but we want to then know how many are outside, so it's the same question, of course, as counting how many are inside, and then subtracting from 9. So the solution to this problem would be, so of course we take, we consider this closed unit disk, so everything that's inside here.
Professor?
Yes?
Don't we need to consider if there's any zeros on the disk itself?
Yeah, you're right. To apply this this theorem, you need to do this. Hang on. So what you're saying is that you're saying this even for the statement of the theorem, right? Even in the statement of the theorem, it doesn't say anything about that. You agree?
Yeah, but you said that we will subtract zeros, and like we have something we didn't consider. Like it has 9 zeros as a plane.
Yeah. Okay. Yeah. So I think, so I have to make a remark. Anyway, to address this kind of question, let me make a remark. I can write it here. But an important remark about this this condition here. Okay, so assume that this is true. And okay, again, so I will tell you what I will choose for f so that this is clearly true. So I will choose it to be 5z cubed. And then you can check that this condition will hold. Okay, so actually, yeah, I will give a remark in a second. I'll just tell you what I want it to be what. So then, so I choose f like this on the disk. And then let us just check first that this holds, so everybody's convinced. So this one is then equal to absolute value of z9. This one disappears, plus 2z plus 1. And this one is less than or equal to absolute value of z to the 9 plus 2 absolute value of z plus 1. But where are we considering this estimate? Well, we are considering on the unit disk, right? Oh, on the unit circle, sorry. So absolute value of z is equal to 1 here. So this thing is equal to 4. 1 plus 2 plus 1. And 4, we need to compare with the absolute value of this thing here. So this is less than or equal to 5 times the absolute value of 5z to the 3. Okay. So we see that this thing holds, at least. This is the first thing. And now that I wrote that, let me now tell the remark that relates to your question. So now we make the remark that from this condition, let's call it condition star or something like that absolute value of f minus g is strictly less than absolute value of f. So from star, f and g cannot have any zeros on gamma. Okay, so why is this? So this relates directly to your question, right? So I will then have, by just checking this condition, I will have indirectly checked that there are no zeros on gamma. So the reason for this is that if f had a 0, then because absolute value of, so let me just write it here. So if f had a 0, then this would be 0. So what's on the left-hand side would be absolute value of g is strictly less than absolute value of f, which is then 0. So then the condition star would say that absolute value of g is less than 0, but this is, of course, a contradiction. This little thing here means contradiction. And on the other hand, what would happen if g of z is equal to 0? Well, then we put this here, and then it would say that absolute value of f of z is strictly less, right, than absolute value of f of z. And this is, again, a contradiction. So this shows that as soon as you have this kind of strange condition from the statement of Residue theorem, there can be no zeros on the boundary of the disk in this case itself, but on the curve gamma itself. Okay, so this should answer your question, I think.
Okay.
Yes, but excellent question. Thank you. So now let's conclude this thing, this theorem. So just by Rouché's theorem, we have now checked that everything applies. So F and G have the same number of zeros in D, which is what? So then we just have to remember that F was 5 to the Z, 5 times Z cubed. And we chose this, of course, so this condition has to hold, but also, and this is of course the trick to choose correctly F and G, but it's clear that this one has, of course, 3 zeros inside. So 3 zeros now inside the disk, which means that we have 6 zeros outside because there were no zeros on the boundary itself. And so then we have found an answer to a, I think, highly non-obvious question, if you just ask it like that, how many zeros could such a polynomial have outside the unit disk? Well, 6, as it turns out. But I think this is not, I don't know, just looking at it, I wouldn't be sure if I had just a guess, just like that. Okay, and then we have the matter of the proof of Rouché's theorem. The proof. So we already saw that F and G have no zeros on gamma, for the same reason I just explained. Moreover, if you look at the following quotient, so from this condition that we had, the condition was, F down here. So the condition was that this was strictly smaller than this one. It means that this thing is strictly less than 1. But it's also equal to, I can also just rewrite it like this. Okay, so it's strictly less than 1, this thing. And now the idea is to apply the argument principle to the function f of z given by g of z over f of z. And now you're telling me, okay, but this might be meromorphic or something. Well, that's totally okay. So remember that for the argument principle, we were working with a meromorphic function. So the fact that f might be 0, it's okay. So we apply the argument principle to this. And we let sigma be the image curve. So again, in the statement of Rouché, we had some closed curve, gamma. And we let sigma be the image curve, but under the capital F, where F was this G over small f. And then, now we're going to use this geometric interpretation, that we had in this example with on the right board here, where we're trying to find how many times this 5th degree polynomial was winding around 0. We're going to do something similar, but in a purely theoretical setting now. So we're going to look at this winding number of sigma around 0. Well, we know from our previous remarks that this is nothing but capital F prime over capital F of z, dz. And that this, writing it correctly, so I reiterate that you have to sum over all the zeros and up to multiplicities. So this is the sum of this minus the sum of poles. So I will write this. So these are zeros of f over g, okay, and these are poles of f over g, okay. So let me erase this this board. Okay, so this is equal to so the number of zeros of g over f minus the number of poles of g over f. But, you know, if you have, I mean, inside of this of gamma, so in gamma, that's the name, so in gamma. But now, how can we tell the number of zeros of g over f? Well, this is exactly the number of zeros of g that are not zeros of f. And again, inside gamma. And this is the number of zeros, number of poles, sorry. But I can also write it the number of zeros of f that are not zeros of g inside gamma. Okay, so if I take the difference between these, then what do I get? So I want to show that this equals 0, because what I'm picking up here is I want to show that that f and g have the same number of zeros inside gamma. So here I have the number of zeros of g that are not zeros of f, and I have the number of zeros of f that are not zeros of g. Okay, so for that we have to interpret, again, this condition up here. Call it double star, since we already used the single star. So now we use that this condition double star, means that if I look at this sigma of t, which is f of gamma of t, then where is it? So it means that it's in this disk, right? Centered at 1 and with radius 1. Here is 1. So this sigma, this curve, is doing, I don't know what it's doing, something very complicated possibly, but it's always doing it inside of this curve, which means that it never winds around 0, right? So this implies that this winding number has to be 0, and we are done. We are done in the sense that we have proven that we have the same number of zeros inside gamma. Okay. So I hope that's all right. So in the little time that's left, I would then like to propose that we start looking at this topic of real integration. Unless, of course, there are some questions first. Okay, anyway, so now we've covered the argument principle and the Sjöström theorem. So now you should be able to do also these parts of the homework, and you have seen these things. And as usual, of course, the idea of the homework is to be complementary to the lectures, so it will hopefully have you go through things that we do not go through in detail here. And the same, so the homework has 3 integrals, could have had even more, but okay, it has 3 so far. And it's important that you go through all of them so that you really get a feel for this integration. So applications of this residue calculus to real integrals. So I'm just guessing this is something that all of you have seen, but you can never be sure. So just the idea here is very simple. So the idea is that the residue theorem allows you to integrate along any closed curve gamma, and it gives a nice formula of how to compute these integrals along such a gamma in terms of the zeros and the poles of a function inside of the region enclosed by this curve. Now, in the special case of a real integral, so what we do in real analysis is that we consider integrals on the real axis, right? So this would just mean that in real analysis we would consider integrals on here. And in order to compute this integral using the residue theorem, well, the problem is that this is not closed. So then we have to make this part of a closed curve in the complex plane and then take into account the integral around this extra part. So a very common choice would be this, but it's by far not the only choice. Okay, so this was just a very quick preliminary discussion. And what's important to say now is that, there are these 5 types that I mentioned last time of integrals in Alfors. I really strongly urge you to go and read and go and study this chapter if you have access to this book. If not, then maybe you can share it with each other if somebody has. But I will also try to put more in the lecture notes when I will have time to go through here. Some more examples. So what we'll do in the actual lectures, because I want to prioritize some other topics towards the end of the course, rather than this. So in the lectures, I will give some examples and very quickly point out some key points. But then if you don't actually go home and do some work on this, then of course it won't stick. And as with computing integrals in real analysis, applying the residue theorem is much a matter of experience. So you really should get this experience, which will teach you what contour should I choose, what substitution maybe should I make, and so on. So with just a little bit of practice, this shouldn't be a hard aspect of the course, but it just requires you to sit down and just try out a couple of them. So try all of the ones on the homework and try a couple more, right? For example, work through the ones I will give in the lecture notes. So I told you there is a systematic way of categorizing real integrals into 5 types. But first, and what I will do today, is just to give an example of, let's say, medium to easy difficulty of such an integral. And then next time, I will just give a very quick overview of these types, but also try to start another topic. So, yeah, because, the 15-lecture course, and we had some delays, essentially, due to this writing on the iPad and whatever, being a bit slower. But we are more or less on track. So the example that I want to consider is, now to make this concrete, is the following integral. So I think I wrote this down as an example earlier. So we want to show that this integral is equal to pi divided by e. And I don't know if you recall, I think I made this remark earlier, but this is, so it's an integral that arises in probability theory and so on. And it's a Fourier transform, actually, of a suitable function. But the point is that this cannot be evaluated with just standard first-year methods in in calculus, right, from real analysis. So this is really something where it makes some sense to try and apply the residue theorem to these things where they cannot be evaluated by simple other methods. But using the residue theorem, it's not hard. So now, to compute using residues, so what do we do? So the first step is so we want to consider now a holomorphic function whose restriction to the real line is the integrand in question. Okay? And what function would that be? We are interested in this part. This is r. This is minus r. And then, you remember that the integral from minus to infinity of some f is defined as the limit as r goes to plus infinity of the integral from minus r to r f of x dx. So we want to look at some function which coincides with the integrand here on the interval minus r to r. Okay? So again, what function should I consider? Because I want something to apply the residue theorem, it should be holomorphic also everywhere that I consider. So, any ideas? Maybe you think it's a too simple question or something? I would understand. Okay, so I'll tell you then. So we just consider the same function, but with now z a complex variable. So this one is, it's a meromorphic function. On C. And then we have to understand where are the poles of this function in order to apply the residue theorem. So what are the poles of this function?
Plus minus I.
Plus minus I, yeah, exactly. So the poles are when z squared plus 1 is equal to 0. So z is plus minus I. And then we consider a suitable closed contour. Gamma r, which is then this circle here. So this one is IR. Okay, so this one I call gamma r. The whole thing is gamma r. And I will call this line segment minus r to r, and I will call the circle part CR. So the total thing is then CR plus minus r to r. And I'm interested in the integral along this straight part, but I'll use the residue theorem to compute the whole thing and then subtract what happens on the large circle. And here r is larger than 1. So, okay, so there's one pole. Yeah, so let's take just r usually much larger than 1. So we'll want r to go to infinity. And then we note that we have these two poles. When we want to apply now the residue theorem, to compute this integral, we have the pole I inside, and then we have the pole minus I, which is outside. So the one outside, it doesn't even contribute to the residue theorem. So the only thing you have to take care of are the poles inside the curve. So only the pole z equals I is inside. So we can forget about z equals minus I. And so now we just apply the residue theorem. And in order to do that, we want to know what is the residue of f of z in z equals I. And then if you remember, we saw a formula last time. So the formula was, so by the way, so this is a simple pole, right? So simple poles. There is no multiplicity to these poles. So you remember that we had a formula like this. That the residue is equal to this. It was a formula we saw from last time. In general, you'll have to multiply by some power here, and so on. But since it's a simple pole, because it's a simple pole, we have this formula. And this is equal to what? Well, we had this function which was, so of course the denominator varied factors. So this is equal to e to the iz over z plus I. And this should then be simply evaluated by continuity in z equals I. So this is equal to e to the I squared divided by 2I, which is equal to e to the power minus 1 over 2I. Let's write it like that. Okay, so by the residue theorem, what we get is that the integral along gamma of f of z dz is equal to 2 pi I. So we just had a single pole inside, so the residue of f at I, which is then equal to 2 pi I times this 1 over 2I e, which is then the 2I cancel out, and it's equal to pi over e. Okay? And now we have the remaining steps. So would be done. So by the way, this is independently of R. Okay, so independent of this R as long as R is larger than 1. And now we would be done if only what? So if only we could show that the integral along the circle part tends to 0 as R tends to plus infinity. Okay, so why is that? Well, it's because we know that the integral that we're interested in is this, which is then equal to the integral along gamma r of f of z dz minus the integral along CR of f of z dz. And then actually the one I want is when I put the limit as r goes to plus infinity, then this would be equal to I. When I put the limit, then this, because it's independent of r, then this is going to be pi over e. And when I put the limit here, I want to show that this part will be equal to 0. And to do that, so this is a very important sentence here. So this one will be done by something called Jordan's lemma. Okay? So in order to do things like this rigorously, we use something called Jordan's lemma, which you definitely should remember, strongly advised. So I will just state that, and then we'll go for lunch. So Jordan's lemma is the following. And by the way, so when we are choosing the contour and we choose this semicircle part, we're doing this, I mean, we could choose really anything that we could conveniently estimate that the integral along this would be 0. Because, you know, thanks to Cauchy's theorem, I mean, if I take the integral, if I take a semicircle, or if I take a rectangle, or maybe a triangle, or so on, actually the result of this remaining part, which is not along the real axis, it will be the same. Because integration is independent on paths, I mean, up to if the poles are the same inside or not, and so on. But really, this one is chosen for convenience so that we can work with it. You know, you could choose some other complicated curve, but then it would be very hard to estimate in practice. So the advantage is that with the circle, we have the following. So if alpha is a positive real number, and we put this, some notation that we saw some lectures ago. So MR, let it be the maximum of the absolute value of some function that you have, g of z, on absolute, under these two conditions. So this means simply maximum over this part, right? So maximum over CR. So you want the maximum of the absolute value of your function g. And assume that it's equal to MR. Then you have that the integral of g of z e to the I alpha z dz, which is exactly what we have, right? In our case, g is equal to 1 over z squared plus 1, and alpha is equal to 1. So then this is less than or equal to pi over alpha times MR. This is Jordan's lemma. Okay, and so applied to our problem, to our integral I, we have g of z is 1 over z squared plus 1. Alpha is equal to 1, so that f of z is equal to g of z e to the I alpha z. And then this implies that absolute value of our integral along this curved part is less than or equal to pi mr, where mr is the maximum so the maximum along this half circle, which I could say the maximum when the argument is between 0 and pi, of 1 over z squared, but z squared, I write it now in the exponential form as r squared e to the I times 2 theta. And this one, actually, so you can check that it's equal to this, and that this goes to 0, of course. I mean, it's equal to this. So our integral here is less than or equal to pi divided by r squared minus 1, which goes to 0 as r goes to plus infinity. And we said over there that you know, we already got the I equals pi over e minus the limit as r goes to infinity over whatever contribution this has. And now we have shown that the contribution had to be 0. And therefore, we conclude the first example by saying that the integral is equal to pi over e. And now as a last remark, maybe if I put instead of e to the ix, if I put sine x or cosine x, then I claim that I've already automatically computed them. Why? Any idea? Okay, so I know that this integral e to the ix over x squared plus 1 is equal to pi over e. And we note that this is a real number, right? And this is equal to the integral, so e to the minus x is just sine x plus I cosine x. Sorry, cosine x is the real part. I think I said it wrong. But plus I times this. So we have this real number pi over e, which is equal to this integral plus I times this integral. And this implies that this thing here is equal to pi over e, and this thing here should be then equal to 0. And so on. So the point here is that whenever you see an integral with sine or cosine, a real integral, often this means that you can just compute this one, e to the ix, and it falls into the same category. And it's very crucial that you use Jordan's lemma. And in the notes, I have a proof of Jordan's lemma. It's not complicated. It's 1 page. So you should read the proof of this. And next time, I'll finish with a more systematic approach of this. But hoping that you are already a little bit experienced and that you will get some compliment and a lot more practice also in the tutorials of this. So this is what I'm banking on. If it turns out nobody has ever seen any residues before in your life, then maybe I'll change my approach, but then you should tell me. So. Okay, any questions about this before you go for lunch? So can I just ask, I mean, have you all seen a lot of these integrals computed with residues before?
Yeah, I took them in my undergrad years.
Yeah, so usually people do, yeah. Exactly. So did someone, and I mean, usually people come here and we already took complex analysis, but somehow we still do this course, which is like a first complex analysis course, but we try to do it a bit, you know, a bit better and to do things that we haven't seen. But usually, if I'm right, I mean, my impression would be that most people in undergrad, they see especially a lot of applications of the residue theorem, and they see less of the other things, which is why I want to do the opposite in this course. So this is what I am assuming. So please tell me if the assumption is wrong. Okay. So any other questions? Or any other questions? Any questions? Okay, good. So then I think you should have, oh yeah, one more thing, by the way. So I should mention, just for the homework, that when you have an integral of the logarithm or the square root or some power function, then you have a branch cut, right? And the way you choose your contour when you have to deal with this branch cut is, you know, a bit special, and this is maybe the only slightly tricky thing when you do this integration. But since I think the integral I ask you to hand in from the homework is one of those, I should still tell you that when you have branch cuts, so for example with log of x or the square root of x or x to the power alpha, where alpha is some real number, then what you have is, so a very typical contour, so let me just say, so I can draw the typical contours actually. So the first typical one, the easy one, is this semicircle that we have. Another second typical example is this semicircle, but maybe you have some, maybe you have a pole actually on the real axis. So if you have a pole on the real axis, you have to avoid it. So for example, the pole might be in 0, and then you have to avoid it by going around here on a small disk. And so you look at this thing. And when you have the branch cuts, you will typically use this thing called a keyhole contour. Okay, so you can also Google this for better pictures. This is very common. So the keyhole contour is like a circle, but when I come very close to here, I go in, I go around a small circle, and then I go out again. Hope you can see this. So you have this keyhole contour that looks like this, and then the contribution on the lower part and the upper part will not be the same due to the discontinuity at the branch. And by the way, the last remark is when I draw it like this, I will have to take the branch cut not the standard way. You remember the principal branch would have been to remove the negative axis. But here I actually took the branch cut, so I removed the positive real axis. Okay, so I just wanted to give this, if somebody needs it, just this is some hint for your homework problems, that you can use these contours. Okay, so see you next week. Thanks everyone.